This is my screencast for Chapter 7, entitled Some Mysteries Revealed. And we have some homework to do, and what we'll just cover, we'll review Chapter 6, and then we'll just run through all of the sections of the chapter. So first with Chapter 6, I just wanted to hit a couple of highlights here. First of all, we're recognizing that our general thoughts about how heat transfers from a so-called hot thing to a cold thing seems to match what's going on with the microstates, and more specifically with the natural log of microstates. And so we use this new definition of temperature, which can be done sort of fundamentally. So that was a big deal out of Chapter 6. And then the second one, and this is what we're going to be using quite a bit of for this chapter, is this notion that nature is lazy. And so what we found with the Boltzmann factor, with this e to the minus energy over kBt for the probability, we essentially are finding that the most probable state of any system is to be in its lowest energy state. And that just seems sort of weird, but that's why, for example, all of the shells of the atoms in the periodic table fill up the way they do. Everything goes to its lowest energy state. All right. There we go. Okay, so let's start with the Maxwell-Boltzmann distribution. So we're going to essentially use the Boltzmann function from the previous chapter, and we're going to try to understand how that works for speeds. So the first question is, what is the reservoir? The reservoir is just the rest of the atoms. And so essentially we say that every single individual molecule is in a reservoir of all the rest of the molecules. And so that's usually big enough to answer all of the things that a reservoir needs to do. Now, the issue here is it depends really what you're asking about. And the reason this gets really confusing, you have to be really, really careful about what question you're asking. So here's one question. What is the probability of a particular quantum state? Whoops, the thing moved, I'm sorry. What is the probability of a particular quantum state that happens to have speed v? Very simple. The standard function that we got from last chapter, this e to the minus 1/2 mv squared over kBt, so that's the standard numerator divided by z, which is the sum of all of the possible states you could have. And so that certainly makes it seem as though the most probable state is to be at 0 energy, because the biggest this curve will ever be is when v equals 0. And that's because of this negative sign here. Well, that doesn't seem to happen that way. What we find instead is that if you ask the question, what is the probability of finding something with speed v regardless, and I'm making a joke here about irregardless, of the quantum state. So, in other words, there's lots and lots of quantum states that have the same exact energy. We've seen this before. There was a homework problem in Chapter 6 with 3 upper states and the 1 lower state. And we found that each individual state has this probability up here. So you have to add them all up. And so the way to do it is to say, okay, I know the probability of a particular state. Now I need to know how many states all share that same exact speed. Well, and there's a section in this chapter we're going to skip, but the answer is that it's related to v squared. We've got this probable velocity I'll talk about in a second. But the notion is here's the probability that we had from before, and here's this notion of counting the states. And it ends up being v squared. So for something that goes twice as fast, there's 4 times as many states that go that fast. And again, I'm going to skip the section that sort of proves that. So let's take a look at what this curve looks like. So I'll just go to this link here. Here we go. So let me just make this a little bit bigger here. It doesn't seem to want to make it bigger. Hang on a second. View. Zoom in. Maybe we'll zoom in again. Zoom in again. There we go. Okay, so we have this graph here. And so this first part here, this part right here, is the v squared part. And so it's rising, 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 but eventually it has to roll over. And so it has a peak, and then it has this really long tail. In fact, this tail never exactly goes to 0. What we find down there is that you have essentially the probability of any speed. It's just really, really low. It's highly improbable, but it's possible to have just about any speed at a particular temperature. Remember that this graph is drawn once you know the temperature, because the equation, which is written a little bit differently by these guys, but it has temperature in here in a couple of different places. So once you tell me the temperature of, say, the air in this room, I'll tell you, whoop, there's this many particles that are going this fast, there's this many particles going that fast, there's this many particles going that fast. And so this, by the way, is a nice little website. If you put in something like 14 AMU, which is, what is that, nitrogen gas or something, and calculate it, and then give it a temperature at, oh, say, room temperature, it comes down here and it gives you all kinds of useful information down here with the most probable, the average, the RMS speed, and all kinds of units. So it's a pretty useful website for that. Okay, so let's go back. Where are we? Here we go. So I think I've already covered these important points, but let's see. Let's hit them again. It starts at 0, and then this question. But I thought that was the most probable. It is the most probable for that quantum state, but there's just tons and tons of quantum states that are moving not 0, so you have to count them more. It has a peak. That's probably a good thing. If it didn't have a peak, then it would be problematic because it would just keep growing and growing and growing, and you'd really have a hard time integrating these things. And I already talked about the long tail. Okay. So let's talk about this counting velocity states section. Well, we're pretty much going to skip it. In the next online class in the spring, we're certainly going to talk about how you can't just have any old kinetic energy. There's only certain kinetic energies you can have if you're a particle in a room. And once that happens, once it's countable, then you can do what's happening in that section 7.2. All it's trying to prove is this equation, this portion of the equation right here, this v squared portion. It happens to give you some of the 4s and the pi's and all of that stuff too, but the really important thing is the v squared. Okay, so let's look at the average energy of a quantum system. Well, why might we care? Well, we'll care in the later sections, but this section is really just a math thing. It's just a different way of calculating means. So I just made up some numbers here. So let's consider data about families and with various numbers of kids. So I just made up some numbers here. Let's say there's 34 families that have no kids, there's 45 families that have 1 kid, 76 families that have 2 kids, all the way up to 7 families that have 5 kids. I just made these numbers up. Okay, so let's ask some questions. The first question is, what is the total number of families involved? Well, the total number of families involved, you would just add up the all of the numbers of the family. So adding up everything in this row here. So if you do that, 34 plus 45, blah, 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 there were 210 families in this made-up study. Okay, so that's fine. And then, but here's the next question. How many total kids were involved in this study? Well, if there was 45 families with just 1 kid, that combines for 45 kids. If there was 32 families with 3 kids, let's see if I can do that math in my head here. 32 with 3 would be 96 kids involved there. So as we move on out here, we see that you get a total of 396 kids involved. But I want to be very clear that this is the equation we're doing. You multiply, this number by that number, 0 times 34, and 1 by 45, and I'm writing it this way, that the ith number of kids and the ith number of families. Okay, so what is the average number of kids per family? Well, that's just going to be the total number of kids divided by the total number of families, 1.89 for this example. And this is exactly what we're doing here. The numerator was well, now I'm switching back to energy. The energy and the probability of having that energy divided by the probability. So this is the number of families and the number of families down here, and this is the number of kids. If you write the probability in terms of the Boltzmann constant, you have to replace it with that right there. But be careful. The last equal sign only works if you're summing over quantum states. Because if you're summing instead over velocity states, you have to use the stuff that we've developed earlier, this here. So you have to be really careful how you're counting everything up. Okay. So let's apply it to the Einstein solids. So just a few major points here. Let's see. So there's an infinite number of terms in both the numerator and the denominator for the Einstein solid. However, they follow a very, very simple pattern, and that's why we're able to do some of the math here. Okay, so what happens at low temperatures? So at low temperatures, the chances of being in any state other than the ground state are pretty low. because what you're saying here is that at low temperatures there's just not that much energy around. The chances of a molecule or oscillator to even move up one step, pretty slim. Okay, and so if almost everybody's in the ground state, the average energy per oscillator is pretty low. Now at high temperatures, you got gobs of energy around, so the chances of being in a few states, not just the ground state, is finite, and so the average energy starts to rise. Now at first you might think that that energy should keep going up and up and up, but it does plateaus. Here's an example of the curve here, so I'm talking about this section right here where it's rising, 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 but it starts to plateau. But note here what the y-axis is. It's the average energy divided by temperature. So yeah, the average energy does keep growing and growing, but we keep dividing by a bigger and bigger number here because the x-axis is just the temperature as the temperature goes up. Okay, so we say at the low energy we're pretty low, at the high energy it plateaus, and just in between there needs to be a transition. And then also note that they're also using that eBoltz program there. Plotting the heat capacity, very similar structure, just doing derivatives instead of sort of finite numbers, and you get pretty much the same thing. By the way, here's our calculation for the Einstein solid. This is where those infinite sums are, but it turns out you can do them. Okay, so how do we apply that? Well, the very last section generalizes that result. Here's the main points. Every mode of energy can be treated independently. This is very subtle. I would take a look, if I were you, at T7A.2 to see that there's some subtleties there. But we're essentially saying first, let's see, first the translational energies get turned on, then the rotational energies get turned on, then the vibrational energies get turned on. We treat them all separately. But no matter what it is, every single mode of energy is quantized, so that's very important. And we say, okay, so there's this transition temperature. Well, that's kind of the temperature where finally it's hot enough in the room or hot enough in the box or whatever that a few more than just the ground state will be populated. Okay, but if you're colder than that, if it's really hard for the molecule to get bumped up one, then that mode of energy is not going to contribute much to the specific heat, or also known as the heat capacity. So there's very little contribution. I think the book does this really excellent example. It says, look, if the space between the ground state and the very next state you're allowed to be in is, let's say, 17 times the Boltzmann constant times T, so in other words, it's really, really far up there, the chances of a single molecule getting smacked hard enough to jump up that high are just so slim. So they just don't bother doing it. They stay down in their ground state. Then you can sort of rank them. Translational has the lowest spacings between them, rotational has the next highest, and after that comes vibrational. And in fact, vibrational has the highest transition temperature, so it tends to be frozen out of the heat capacity.